All right, now let's talk about instantaneous velocity. So very similar to the rule we were looking at earlier, when we were looking at the instantaneous rate of change, the instantaneous velocity will be found by using the limit as h approaches 0 of f of t plus h minus f of t all divided by h, where v of t is a instant velocity. So what we found is the instantaneous velocity of function f over time, provided that the limit exists. So let's take a look at example 4 here. It says tourists standing on a 300-foot tall viewing tower often drop coins into the fountain below. The height of the coin falling from the tower after t seconds is given by this equation, where this is the height, original 300 minus 16t squared. That's the effect of gravity on any object, and feet, that is, feet per second squared. It says find the instantaneous velocity, v of t, of the coin at 2 seconds. And so here's the idea. We want to find the instantaneous velocity, and according to the formula in the previous slide, that would be equal to the limit as h approaches 0 of this function h of t, which is not a fraction. So let me write this as 300. Oh, no, I am right. Fraction. We need to write f of, what we're looking here is h of t plus h. I'll just write it out in function notation first. T plus h minus h of t. That's going to be our formula. So let's plug in, see what we get here. The limit as h approaches 0 of, okay, if we plug in a t plus h, we get 300 minus 16 t plus h quantity squared minus, and now I'm going to use these other brackets here, h of t. Should be just 300 minus 16t squared. All of this would be divided by h. Okay, so now let's go through simplifying. Whoops, that's not what I want to do. All right, so if I go through to simplify, what I will have here, the limit as h approaches 0, we will have 300, and I need a FOIL. So let's figure out what t plus h times t plus h is. So when I FOIL this, I will have t times t, which is t squared, t times h, so I'll say ht, plus another h times t, another ht, plus h times h, which is h squared. So we would have 300 minus 16 times t squared minus 2ht, no, plus, not minus, I'm sorry, plus 2ht plus h squared. And then when I distribute this next portion here, I'll distribute the negative through here, minus 300 and minus a negative would be a plus 16t squared. All this divided by h. And so right away, I can see that some values will simplify here. We have a 300 minus a 300. That'll go away. And when I distribute this through, I'll have a minus 16t squared, and I have a plus 16t squared there. So these two values, when I distribute that, will simplify. And that would leave us with the limit as h approaches 0. When I distribute here, I'll have a negative 32 ht and a negative 16h squared all over h. So I see that there's a common denominator here, or not a common denominator, sorry, common factor in the numerator. So this would be equal to the limit of h approaching 0 by GCF, that h out of there, greatest common factor it. I could actually pull out a negative 16 as well, negative 16h. That would leave me with, if I divide this by negative 16h, that would leave me with positive 2t. And then since I pull out the negative 16, it would be plus 1h, plus 1h, all over h. We can see here that these h's will simplify with one another. And so I can just directly substitute this in. I I guess I didn't have to take out the h because I'll end up distributing this right back here. It'll be a negative 32t. Negative 32t. And I'm putting in a 0 here for h. So it'd be a negative 16 times 0, which that simplifies. And so it seems to me the velocity vector via t will equal, not the vector, I'm sorry, the velocity function would equal negative 32t. Now that's the equation here. So if I want to find it at 2 seconds, what's the velocity of the coin after 2 seconds? It would be negative 32 times 2, which is equal to negative 64. Like I mentioned before, this is feet per second. That's feet, and this is per seconds. So this would be negative 64 feet per seconds. Would be the velocity at time 2. Now, if you are wondering, what does this velocity vector have to do with this? This is the tangent line. Let me make that connection for you. If we looked at h of t being 300 minus 16t, and I'm going to set this to where the highest or the lowest value is going to be negative 10, and we're going to go up to 350 so we can see above this graph. There we go. And let me change the x-axis. We don't need to see that far wide. We'll say from negative 5 seconds to positive 10 seconds so you can get an idea of this parabola here. What we found out is our velocity vector via t equals negative 32t. And so that's the speed at which you can find that the value is falling. So at 2 seconds, we said it's negative 64. So at 2 seconds, which is right here, the slope of this line at 2 seconds would be negative 64. Let me kind of show you here. Y equals negative 64. And let me change the color here in this tangent line so you can see what I'm doing. Negative 64x. And if I want this to be at 2 seconds, and at 2 seconds, it looks like this graph has a height of, if I get there exactly, 236. So to be up 236, I'd say minus 236 there. And x to go right 2 needs to be minus 2. You can see that is the tangent line. So it's falling at 64 feet per second at that point. That's right 2 units, meaning 2 seconds, and at a height of 236, because that's what the height would be at that point. You can see how it's a tangent line. That is the instantaneous velocity. So that's how the graph there corresponds with what we were learning about tangent lines. The tangent line is the instantaneous velocity or rate of change at that point.